So now we're going to be looking at describing and explaining Newton's third law of motion. We're going to apply Newton's third law of motion to find velocities. And then probably the trickiest part of this lesson is going to be an application involving what we call reaction forces. So just to review things here, Newton's first law of motion is an entirely qualitative thing. There's no calculations involved in Newton's first law of motion. It just says that whatever velocity an object has, it will maintain that velocity unless there is an unbalanced net force. So we can kind of tie this together with Newton's second law by simply saying that the first law says if F net is 0, then the acceleration is 0. That's really what Newton's first law of motion says. And if F net, I'm not going to write it down, but if F net were not 0, which means there's an unbalanced force, there would in fact be an acceleration in the direction of the force. What Newton's second law of motion does is just gives us a formula that we can use to determine the acceleration from the net force. And I was a little sloppy here in your handout, or at least what you're looking at on the screen. I don't have vector symbols above the force or the acceleration, and I probably should. Newton's third law of motion talks about something we kind of ignore most of the time. When we talk about Newton's first and second law of motion, we always talk about the object in what we call isolation. So, for example, when I drop an apple, if I have an apple, and because I'm not a very artistic person, this is the apple. When I drop that apple and it falls through the air, what we do when we analyze its motion is we draw forces acting on it. And there's really only one force. It's the force due to gravity that's acting on the apple. So we would say that the net force on the apple is the force of gravity. And I don't want to get buried in a big explanation of gravity just yet, because we're going to study that later in this unit. But the fact of the matter is, a gravitational force is exerted on the apple by the Earth. And what really happens is the Earth and the apple are attracted to each other. It's very hard for us to visualize this, but when I drop an apple, here's the Earth. When I drop an apple, there is a force acting on the apple towards the Earth because the apple is attracted to the Earth. But the fact of the matter is, the apple pulls the Earth towards it. This is what a force of gravity actually is. A force of gravity is an attraction due to gravitational properties of matter between two objects. And in this case, the apple and the Earth are attracted to each other. Now, there's a reason why we only analyze the forces on the apple, because if I asked you what the net force acting on this whole system is, the net force acting on this entire system is 0. There is a net force that's not 0 acting on the apple towards the surface of the Earth, and there is the same net force that is not 0 acting towards the apple on the Earth. So the apple is pulled towards the Earth is pulled towards the apple. Those two forces are equal. Those two net forces are equal. By the way, that MA of the apple has to equal MA of the Earth. Those two net forces are equal in magnitude. And the reason why when you drop an apple you don't feel the Earth rushing up towards you is because its acceleration upwards is very, very tiny. When I push on a vehicle that's stuck in the snow and I finally get it moving, the fact of the matter is, however many newtons I'm pushing forward on the car is pushing with that many newtons backwards on me. And we don't often talk about those forces because they're not usually useful. But this leads us to Newton's third law. When you have one object exerting a force on a second object, then the second object exerts a force on the first that's equal in magnitude but opposite in direction. I think the old adage that you are taught in maybe junior high or elementary is that Newton's third law says for every action there's an equal but opposite reaction. That may ring a bell. So that's what Newton's third law is. And we're just going to plow right into some examples here. While standing on a horizontal frictionless surface, and I know we kind of laugh, high school physics, oh, frictionless. We will take friction into account once we understand the basics. So we're just going to imagine here that you were on the slipperiest surface possible. You're on an ice rink and it's melting. It turns out that water on ice is incredibly slippery. You're standing on a surface, you have a mass of 50 kilograms, and you push on a wall with an average force of 125 newtons for 0.10 seconds. What's the velocity after that time? I would be willing to bet that many of you can do this question without even thinking of Newton's third law. But when you apply F net equals ma to this situation, in order to find the speed of the student or the velocity of the student, you need the acceleration of the student, which means this is the force on the student. And what I'm about to explain is, no doubt about it, picky. This is very, very picky, but it's important. This acceleration will be of the student. So here comes the picky part. That 125 newtons east is the force on the wall. That's not the force on the student. The force on the wall is 125 newtons east, which means the net force on the student is 125 newtons west. I mean, it's the same number, but Newton's third law says it's the same number because the two forces are equal in magnitude and opposite in direction. So where we're going with this is we're going to use, I'm just going to highlight west because I don't want to put a direction in the formula. We are going to use F net equals ma to get 125 newtons equals the mass of the student, which is 50 kilograms, times the acceleration, well, the magnitude of the acceleration. So do me a favor here and just see if you get 2.5 meters per second squared for the acceleration, and we do. Excellent. So you get 2.5 meters per second squared by dividing 125 newtons by 50 kilograms. Now what this has turned into is a kinematics problem. This is why I was really, really hard on you guys in the first unit, saying you got to know how to use these formulas. The student starts from rest. They're just standing there. The word standing means not moving. So their initial velocity has a magnitude of 0. The time is 0.11 seconds, and we want to find the magnitude of their velocity afterwards. We can throw the west on when we're done. So it's looking as though the formula that we're going to be using would be A equals VF minus VI over T. So the magnitude of the acceleration will equal the magnitude of the final velocity minus the magnitude of the initial velocity divided by the time. The initial velocity is 0, so what we end up with is 2.5 meters per second squared equals the final speed over 0.11 seconds. Cross multiplying would give 2.5 times 0.11, which I believe is 0.275. Excellent. So the final velocity is, well, the final speed is 0.275 meters per second. The velocity then, which is what we are asked about, is 0.275 meters per second west. So really, kind of the only thing that's different about this is you had to use Newton's third law to determine the force on the student. Let's take a look at the next question. This gets a little more tricky because if you think you have a handle on this and you start looking at all the formulas on your formula sheet, you kind of run into a dead end. This will be the first example where we have to use an algebraic approach without numbers in order to come up with a strategy. So we have a 75 kilogram student standing on a frictionless skating rink. I know, it's lovely. So we have this student standing here, and they throw a 5 kilogram object. So there's an object in their hand, and the 5 kilogram object is going to move to the right, while east at 10 meters per second, and this is 5 kilograms. What we're talking about here is a very important idea in Physics 30. And it has to do with something called momentum and impulse, but I want to just review common sense with you. If you've ever fired a rifle, you know enough not to take the rifle and hold it in your hand so that the butt of the rifle, the wooden stock of the rifle, is 3 inches away from your forehead. Because when you pull the trigger, that rifle has a kickback. And the reason it has a kickback is because of Newton's third law. When the bullet leaves the rifle, it leaves the rifle because the rifle pushes the bullet forward, and that means that the bullet must push the rifle backwards. So the result here is, as soon as the person releases this, I know it looks like they're throwing it in a very awkward way, but as soon as they release it, what's going to happen is that this 75 kilogram student is going to move backwards at some speed. Now, if you look at what I've drawn, it should kind of be common sense that the speed that the person moves backward at will be significantly less than the speed that the 5 kilogram object moved forward at. But here's how you, and I have a feeling some of you could figure out the answer to this question without doing what I'm about to do. Here's how you do this question. You say that the magnitude of the net force on the student is equal to the magnitude of the net force on the ball. Now look at what we have to put in. We have to put MA here, but of course this is for the student. So I'm putting subscripts here. The S stands for student. And on the other side I have m of the ball times the acceleration of the ball. Now how does that help us? Well, acceleration is VF, I guess I don't need the absolute value signs, is VF minus VI over T. So on the left-hand side, that's the student. I'm not going to write subscripts in all of this because it just gets too cluttered. I do want to clean that up a bit, though. We're going to have VF of the student minus VI of the student over T. And then over here we have the mass of the ball, and then we're going to have VF minus VI of the ball over T. And here's the thing that's important. The two times are the same. The two times are the same for this reason. And it's wordy, but you need to listen to the words. However long the ball is being pushed by the student, it's the same period of time that the student is being pushed by the ball. The force on the ball and the student start when the student exerts that force, and they end when the two objects separate. And if the times are equal, we can cancel them. So these times cancel. And by the way, VI for both of these objects is 0, so we end up with a very interesting statement. The mass times the final velocity of the ball, and the mass times the final velocity of the student are the same. Did anybody, I'm just curious, you can either signify because some of you have your cameras on, or you can type. Did any of you get an answer here without going through that rigmarole? See, because what some of you might have done, we can try this, is take the 75 divided by 5. What's 75 divided by 5? I believe it's 15. Okay, good. And what you could then say is, since the ball has 1/15 the mass, the student will accelerate at 1/15 the rate. The ball is going to accelerate quicker. But let's put the numbers in and see what we get. And you can memorize this from now on in this situation. You can say mv equals mv. But what we end up with is 75 kilograms times vf equals 5 kilograms times 10 meters per second. So we want to calculate VF here. By my count, you can let me know, you get 0.666. I'll give you a minute to calculate that. So you are going to have to take 5 times 10. Did I get those numbers right? I'll check. Yep. 5 times 10 divided by 75 is 0.6666. What you get? 0.6 repeating. Thank you. So we're just going to round that to 0.67 meters per second. But the answer to the question is it will be 0.67 meters per second. Now, what's the direction? Well, the ball was thrown to the east, which means the answer to this question is the student will move initially with that speed west. Before we move on to what I believe is one of the most difficult concepts, well, actually there's 2 more. Before we move on, any questions with that example? All right, number 3, a same situation. A 60 kilogram student throws a 5 kilogram object to his left. During the throw, the object is accelerated horizontally through a particular distance to some velocity. What is the velocity when the object is released? So let's break this down. We've got a 60 kilogram student and a 5 kilogram object. The object is accelerated through a distance. So this is the acceleration or the kinematics of the object. It experiences a distance of 0.55 meters from rest to a final velocity of 6.7 meters per second. And what we want to determine is the velocity of the student when it's released. I think you need to recognize something here, that a lot of the time you're given information that's not relevant. The fact that it was horizontally moving through a distance of 0.55 meters per second doesn't change the fact that everything we did here that you're looking at on the right-hand side of your screen would still be applicable to example 3. It's got nothing to do with the distance. Now, if I asked you what distance the student moved, that would be more complicated. But this principle is still true. We can still say that the mass of the student times their final speed must equal the mass of the object. I'm just going to put O for object, times that final speed. And you're told 3 of those 4 things. It's a 60 kilogram student. It's a 5 kilogram object. And the object reaches a speed. This, you may be confused by the VF wording here. This just means that's the speed of the object at the instant the student lets it go. So we can put 6.7 here and solve the problem. Again, had I asked you for the distance that the object, that the student moves, that is more complicated. So we just need to take 5 times 6.7 divided by 60. Which gives me 0.56 meters per second. And it will be to the right because the object was thrown to the left. All right, so now we're going to move on to the final example, which is the most difficult one. If you've taken Math 20-1, there's a number of questions or applications in 20-1 that I describe to students all the time by saying, as I go through this example with you, it will make 100% sense to you. And then all of a sudden, 5 seconds will go by and you'll look at it and you'll go, what are we doing here? What's going on? It's very easy for it to slip out of your mind. The thing I would impress on you is this is a very difficult problem, but it's not, in the big scheme of things, a very important problem. It's not something that if you can't do, you will be unsuccessful in this course or unsuccessful in Physics 30. So there are 3 boxes, A, B, and C. They're resting against each other, and it's on a frictionless surface. That's going to be important. And we apply a force to the box set by pushing from the left with our hand. And as a result, all of these boxes accelerate together at 2.4 meters per second squared. Look at all of the forces we have to find. And you're going to have to make a decision whether you want to write all this or not. Okay? There will be a force. I'll copy this so I have a bigger diagram to look at. On box C, so this is going to get very messy. On box C, there will be a forward force that will be the force on box C due to box B. I'm going to write that down. This is on C by B. And there will be an equal but opposite force on B by C. So I'm not going to draw all of these forces just yet. Let's talk about box C. Does box C accelerate? I mean, look at the question, read the question carefully. Does box B accelerate? Well, the answer is yes, it does accelerate because you're told all of the boxes accelerate at 2.4. Was it 2.4? Okay, at 2.4 meters per second squared. So I'm going to talk now about box C. On box C, F net equals MA. And I'm not going to worry about directions here. Everything is to the right, which means the net force would have to be equal to its mass, which is 4 kilograms, multiplied by 2.4 meters per second squared. So the net force, and this is on C, is equal to 9.6 newtons. Now, that, look at the diagram. That is the only force on C. We're looking at C in isolation. We're not worried about the hand. The only force on C is the one by B, which means this is 9.6 newtons. Box B exerts a force on box C of 9.6 newtons. We're going to go back now and put that into here. Applied on C by B is 9.6 newtons. Now, Newton's third law says whatever force B pushes on C with will be equal in magnitude to the force that C pushes on B with. So this will also be 9.6 newtons. The force on C by B is to the right, and the force on B by C is to the left. Now what we're going to do is look at the forces acting on B. If I look at my diagram, is there a force acting on B? Now look up here, please. Look at the screen. There has to be a force acting on B to the right, and it is a force acting on B by A. This will be on B by A. But the force acting on B by A must be greater than the force acting on B by C because box B moves to the right. This is confusing. What we're saying is that 9.6 newtons of force that we found on C by B means there's 9.6 newtons of force on B by C to the left. And since box B accelerates to the right, there must be another force acting on B to the right that's greater than the force acting on B to the left by C. I think one of the many reasons why this is complicated is you have to keep the language straight. We're talking about 3 different objects, left and right. And then if you confuse the word on with by, on B by A is not the same as on A by B. Now, do we have enough information to calculate the net force on B? Well, of course. The net force on B is its mass times its acceleration. The mass is, this is on B. The mass is 9 kilograms, and its acceleration is 2.4 meters per second squared to the right. I believe that's 24.6, but I would like some confirmation. No? $21.6, thank you. So you get a net force of 21.6 newtons right. Now I could use a formula here or more algebra, but think about this. This is 9.6 newtons to the left. If we want a net force of 21.6 newtons to the right, that means, I'm going to stack these on top of each other so you can see, that means that the net force is this. That force on B by A must be more than 21.6 newtons because we're going to lose 9.6. And again, this net force must be 21.6 newtons, so the force on B due to A must be a whopping, if we add those two numbers together, 31.2. 31.2 newtons. And again, I want to alleviate your fears or anxieties here. I wouldn't get all stressed out over these box problems. They are challenging. These problems are here to get students to think a little bit deeper than you would normally be expected to. And I've mentioned this to you before as well. I do these problems because even though this is a grade 11 course, I am preparing you for post-secondary physics. So, the force on B by A is 31.2 newtons. We can add that to our list. The force on B by A is 31.2 newtons to the right. And that means that the force on A by B would be 31.2 newtons to the left. And then we're going to repeat the process now. We're going to move over to box A, and I'm going to say that this 31.2 newtons on B by A must be equal to a 31.2 newton force on A by B. And again, I feel bad because I can't see your faces, but I want to tell you this. If you're looking at this and you think you've just totally lost it, you don't understand what's going on, that's okay. Most Physics 20 students never really get a good handle on doing this. Now, I'm going to try this in a different way. Does box A accelerate? Well, yes. So there must be another force acting on A. And the force acting on A must be greater than 31.2 newtons, and it must be to the right. So we've got some other force acting on A that is greater than 31.2, and it must be to the right. Now, what is applying that force? The hand. So this force on A is the force on A by the hand. And if you were to take a look at this, that force minus the 31.2 would have to give you the net force. And we can find the net force by taking the mass of A multiplied by its acceleration, which gives 30.8, I think, but I didn't get the last one right, so I want some confirmation. Sorry, 16.8. What am I doing? Okay, 16.8 newtons. So the only way we can get 16.8 newtons forward is if the force on A by the hand is 31.2 plus 16.8 because we lose 31.2. Though don't forget, this is the net force. If I add 31.2 and 16.8, I get 48. Do I? Okay, so this is 48 newtons. And just to drive this home, I'm going to highlight the forces on A. The forces on A are this 48 newtons to the right and this 31.2 newtons to the left. That force of 16.8 newtons should not be thought of as a force on A. That 16.8 newtons is the net force on A. If I asked you to add 48 newtons to the right and 31.2 to the left, you would subtract them and get 16.8 to the right. And what this means is that the force on A by the hand is 48 newtons. And it is to the right, which means that the force, just a second here, I might have reversed the order here. The force on the hand by A would be 48 newtons to the left. A pushes the hand backwards, and on A applied by the hand would be 48 newtons to the right. So don't get hung up on this question. There's going to be one like this in your assignment that I would like you to give a crack, but one final comment. If A is being pushed with 48 newtons to the right, that means this whole thing experiences a net force of 48 newtons to the right. Let's do a calculation here. Let's use F equals ma and put 48 newtons in and put the mass of the whole system, which is 20 kilograms. What do you get for the acceleration? This will be interesting. So we would take 48 newtons divided by 20 kilograms. Yeah, it has to be 2.4, Andrea, because that's the acceleration that everything moves at. So even before you divide them, hopefully you recognize that if we've done everything right, you're going to get 2.4 newtons. Boy, these problems are tricky, but the best advice I can give you is you start with the box at the end and start looking at drawing all of the forces acting on it. I did record this lesson, so I will upload it in a little while to YouTube. I thought I had hit record for the first lesson, but I guess I didn't. So if you need to review some stuff from the first lesson, there's no video record of the lesson. Anyway, you have about 20 minutes left here until the class officially ends. We're not doing number 5. And the reason we're not doing number 5 is because we have not learned about friction. So there's a force of friction in number 5, and since we don't understand anything really about friction just yet, we do not want to do it. For that reason, number 7 on your assignment should be omitted as well because it involves friction. So you have about 20 minutes to work on these 6 problems. Take a look at the examples to guide you through it. You also have some other questions from the first lesson to cover, but I don't think I'm overwhelming you with homework. One last thing, just another check-in. Forgetting about the box question, how was the pace of the lesson? Too fast, too slow, or just right? Don't worry about the box thing. Don't judge your understanding on that. Good, thank you. So everybody take a minute and type too fast, too slow, just right, all that stuff. And I will mute my mic and you guys can get to work. And when you have questions, unmute your mic or type something in the chat, and of course I will help you. You can obviously leave at 11 o'clock, but I will be here till 11:30 every day.